Today we're looking at a geometric interpretation of solutions in 3 dimensions. So looking at solutions of lines in 3 dimensions, we have 2 lines, L1 and L2, both modeled in 3 dimensions, and there are 3 possible solution types. So in a consistent system, we could have one unique solution. So in this case, that's the point P, X, Y, Z. 2 lines are not parallel because they intersect, and they intersect at that one point. A consistent system is where the lines are completely overlapping. So that has an infinite number of solutions for the distance that the lines go on to. 2 lines are parallel and not distinct. The 2 lines are what we call coincident, which is a fancy maths word for they overlap. The third and final case can be split into 2 parts. So these are inconsistent systems, which means there are no solutions. You can have the case where the lines are parallel but distinct. The lines do not intersect and there is no solution. So the other case is where they are still distinct, but they are not parallel. So that's this image down here. And looking at that there, we can see they cross by each other. And whilst they're not parallel, there's still no point in which they touch. So the 2 lines are referred to as skew lines. They don't intersect, and there is, again, no solution. Okay, so determine the unique solution for the system of linear equations L1 and L2 and describe the geometric nature of the solution. So we have 2 lines represented as vectors. So this is your A plus KB, A plus KD, rather, not B. And so looking at this first line, we have D component of, let's call it D1, is negative 4i plus j plus 5k. And then we have D2 component of 6i minus 4j plus 7k. So we want to know if these 2 lines intersect. So we first have to check these values of D. So just a reminder from previous lessons, D is the vector that takes us from one point on the line to a second point on the line. So if you imagine these 2 D vectors, if they're parallel to each other, then they're going along a parallel line. So we want to check, are these 2 values of D, D1 and D2, scalar multiples of each other? So we can check here, what would we have to multiply D2 to get D1? Well, we'd have to multiply 6 by negative 2/3 to get us to negative 4. But if we multiply negative 4 by negative 2/3, we're not going to get 1. So we can see there is no value of m for which D1 is equal to m times D2. So we know that the 2 lines are not parallel. Okay, so to consider whether these intersect then, we want to convert them to their parametric form. So converting these equations to parametric, we get the following. For L1, our parameter is k, so it's not L1 equals, let's do a colon. So x would equal 5, take 4k. Y would equal negative 3 plus k. And z would equal negative 7 plus 5k. So all I've done there is break these into the I, j, and k components, where x is the I, y is the j, and z is the k components. So then for L2, we would have x equals negative 5 plus 6k, y equals 2 minus 4k, and z equals negative 9 plus 7k. What can we do with these values? Well, we want to see if our x values intersect, do our y and z values also intersect? So what is the intersection of x values? Let's let x equal, well, this should really be x1, y1, z1, x2, y2, z2. So we let x1 equal x2. And we get that 5 minus 4k is equal to negative 5 plus 6k. Solving for k, that gives us k is equal to 1. So when k equals 1, what are our y and z values? So y1, when k equals 1, would be negative 3 plus 1, which is negative 2. And z1 would be negative 7 plus 5 times 1, which is going to be negative 2. So we get 1, negative 2, negative 2. What about our z's? So z1, when k equals 1, is going to be negative 6. Sorry. What am I doing here? That should be y2 and z2. So y2 is going to be 2 minus 4, which is negative 2. And z2 is going to be negative 9 plus 7, which was also negative 2. So we can see the y components line up and the z components line up. All we need to know is what is actually the value of x1 that gives us that k equals 1, and that's going to be 5 take 4 and negative 5 plus 6. So our x1 and our x2 are both equal to 1. So we get the two distinct lines intersect at one unique point, and the point is 1, negative 2, negative 2. Okay, for example 32, we want to determine if a solution exists for the simultaneous equations. If so, calculate the point of intersection and hence describe the geometric nature of the system by referring to any possible solutions. So first of all, we have to determine, are these parallel? So let's convert it from parametric Cartesian form into its vector form. So we have x plus 6 over 2, y plus 2 over 5, and z plus 4 over negative 3. All of that is equal to k1. So rewriting that in terms of x, we get that x is equal to 2 times k1 minus 6. y1 is equal to 5 times k1 minus 2. And z1 is equal to negative 3 times k1 minus 4. So what does this tell us about our value of the vector r? Well, that is going to be a take kd, which in this case, our value for a is going to be negative 6i minus 2j minus 4k. All of those are coming from these constants up here. And then our kd is going to be minus k times negative 2i minus 5j. Let's actually move this all down here. So minus 5j and then plus 3, and that's going to be k1, 3k as well. Okay, so looking at this, our value of d is going to be negative 2i minus 5j plus 3k. So that's for R1. Let's now take a look at the second line. So x2 from the second line is going to be 4 times k2 minus 3. y2 is going to be 10 times k2 minus 6. And z2 is going to be negative 6k2. So that's plus 0. So solving for R2, we're going to get, again, let's go back and rename these A1, D1. So A2, take K2, D2 is going to be equal to negative 3i minus 6j and then no k component because the constant in Z2 is 0. And then that's going to be minus k2 times negative 4i minus 10j plus 6k. So looking at our D components, there's probably something that you can notice right away, which is that the D2 is twice D1. So D2 equals 2 times D1. What does this mean? That means that the two lines are parallel to each other. So we know the lines are parallel. If they're parallel, we need to know if they overlap or if they are just parallel without being coincident. So whether they overlap is going to be determined by the x, y, and z value. So we want to find a point on one line and then see if that's also a point on the second line. So let's use the value of k1 is equal to 0. We get x, y, z, 1 is equal to negative 6, negative 2, negative 4. But if we then substitute the value of 0 into the other point, actually, rather than doing that, we want to substitute this in and find out what is the value of k2 when k1 is equal to 0. So substituting negative 6 as x, negative 2 as y, and negative 4 as z into the parametric equations x2, y2, and z2. We get that for all of these. Well, for the first one, we're going to get that k2 equals negative 3/4. For the second one, we're going to get that k2 equals 2/5. And for the third one, we're going to get that k2 is equal to 2/3. So as the values for k2 are not equal, that indicates that the point negative 6, negative 2, negative 4 is not on the second line. So there can't be a solution that exists for the simultaneous system. And the information that we have here is that the two lines are both parallel and distinct. Okay. So moving on from here, we're now looking at solutions of planes. So instead of having two lines intersecting or possibly not intersecting, we're now looking at planes intersecting. So systems of three planes can either have 1, 0, or infinitely many solutions. Two planes are parallel if their normal vectors are equal or a scalar multiple of each other. And then coplanar objects, that's the name we give to objects lying in the same plane. And the three vectors are coplanar if the scalar triple product is equal to 0. So why would having normal vectors that are equal or scalar multiples of each other mean that they are parallel? Well, we know that the normal vector is parallel to the plane. So if you have two parallel lines coming either into each other or going against each other, if they're making right angles with their proposed plane, if they're either in the same direction or in opposite directions, then those two lines are going to be parallel, or those two planes are going to be parallel. And we can sort of see that by the fact that, you know, the Z rule applies here, the C rule applies here. So it means that these planes have to be parallel based off that idea. So let's look at all of the cases. So, consistent system with one unique solution. So, three planes can actually intersect at a single point. So, they only share one point in the middle there. And so, if looking at their matrices, that means A is invertible. The scalar triple product does not equal 0. And then the augmented matrix in triangular form, we see we have a distinct solution for A, B, and C. For an inconsistent system with 0 solutions, we have parallel yet distinct, not invertible. Their scalar triple product will be equal to 0. And we can see there that the augmented matrix in triangular form, we have no ones in our leading diagonal except for the very first entry. So we can find A plus B times A12 and then C times A13 is going to have no solutions possible there. Okay, the other case where we have 0 solutions is where two planes are distinct with parallel normals and the third plane is not parallel. So in that case, A is not invertible. The scalar triple product is equal to 0. And we can see the augmented matrix in triangular form. We do have leading diagonal for the first two entries, but not for C. So the final row is a false statement. How can that be the case when the other two are there? So this system has no solution. Okay, and the other case is where the normals are not parallel, but we still have an inconsistent system, so no possible solutions there. We also have consistent system with infinitely many solutions. So that's if the three planes share the same line between them. And then a consistent system with infinite many solutions going in the... so they're all occupying the same space, they're overlapping, and we can see their matrices and their scalar triple product is equal to 0 there as well. Okay, so considering example 33, we've got these three planes. We're asked to determine the number of possible solutions by examining the normal vectors algebraically. So, determining the normal vectors, those come from the coefficients of x, y, and z. So, n1 is going to be equal to 3i plus 2j plus 5k, and 2 is going to be 1i plus 5j minus 4k, and then n3 is going to equal to negative 4i plus 3j minus 6k. So to determine whether we have parallel planes, we have to check if the normals are parallel. So we can see out of all of these that there's no two normals that pair up to be a scalar multiple of each other. So that means none of the normals are parallel, and hence the planes are not parallel. So no normals parallel, therefore no planes parallel. Okay, so where do we go to next? Well, we want to check what does the scalar triple product equal. If the scalar triple product is equal to 0, then the planes are not coplanar and intersect at a unique point. So the scalar triple product... if the scalar triple product is not equal to 0, the planes are not coplanar and they intersect at a unique point. So the scalar triple product, n1 dot n2 cross n3, can be found by substituting into a matrix and finding the determinant. So we're going to get 3, 2, 5, 1, 5, negative 4, and then negative 4, 3, negative 6. So finding the submatrices of that, we're going to get 3, 5, negative 6, 3, negative 4. I'm saying that in a weird order. Minus 2, 1, negative 4, 6. and then plus 5, and what we're left with is 1, 5, -4, and 3. So finding the determinants of those smaller matrices and then adding that up, we get a determinant of 105. So 105 is most definitely not equal to 0. So we know that they are going to intersect at a unique point. So how can we find that unique point? That brings us to B. Convert the equations to an augmented matrix and then use technology to solve the system. So for B, our augmented matrix is going to be 3, 2, 5 is equal to 27. 1, 5, -4 is equal to -2. And -4, 3, -6 is equal to -10. Solving that with technology, we get 1, 0, 0, 0, 1, 0, 0, 0, 1 as expected, but our right-hand side is -2, 4, and 5. So how do we read this off? Well, it means that the x value is -2, the y value is 4, and the z value is 5. So we have the point -2, 4, 5 is the unique solution. Part C is asking us to describe how the solution can be interpreted geometrically. So the system is consistent and has one unique solution. Geometrically, the three planes all intersect at the point -2, 4, and 5. Okay. For example 34, we've got a system of linear equations, and now we're asked to find the number of possible solutions by examining the normal vectors algebraically. So part A, again, we're looking at the normal vectors. N1 is going to equal -1i minus 5j minus 8k. N2 is equal to 6i plus 9j plus 6k. And N3 is equal to -2i minus j plus 2k. So again, we see that the normal vectors are not parallel. We have no scalar multiple that we could apply to any of these n1, n2, or n3 to get another of the n1, n2, n3. So that means that the planes are not parallel. So no no parallel normal vectors, therefore no parallel planes. Okay, so if a unique solution exists, the normals will not be coplanar. So let's use the scalar triple product and check what the scalar triple product is equal to. So if it's equal to 0, then the three planes are going to be coplanar. And we'll know if we already know that they're not parallel. So it could be planes intersecting in a line, or it could be planes not intersecting at all. So finding the scalar triple product of n1 dot n2 cross n3. This is for part... this is still part A. So the scalar triple product of this can be found by converting it into a matrix and finding the determinant. We get -1, -5, -8, 6, 9, 6, -2, -1, 2. And so again, we find those submatrices, but this time we find that that is equal to 0. So as it's equal to 0, we know that they're coplanar. They're not parallel, so it could be either a line or it could be no intersection at all. To determine that, we're going to look at part B. And so the matrix that we're going to try and reduce here is -1, -5, -8 is equal to -22. 6, 9, 6 is equal to 69. And then -2, -1, 2 is equal to -17. So using technology to reduce that, we get 1, 0, 2, 0, 1, 2, 0, 0, 0, and that is 7, 3, 0. So how to interpret this? It means that x plus 2z is equal to 7, and y plus 2z is equal. Continuing on to part C. So we got those two equations, x take 2z equals 7, and y plus 2z equals 3. We want to represent that in terms of a parametric equation. Z is what we call the free variable because it's not inherently linked. It's in both equations. So we're going to let z equal our parametric value t. That means that x following through from that would be 7 plus 2t, and y would equal 3 minus 2t. And so that would be the parametric equation for the line at which these three planes cross. Part D is asking us, describe how the solution can be interpreted geometrically. So this is a consistent system with the solution representing the intersection of three planes in the form of a line. And that's all for this video. Thank you.